Charles's law, or the relationship between temperature and volume. So here we're going to talk about what happens to the volume of something when you change the temperature of the gas inside it, or what would happen if we squeeze something, or reducing its volume to the temperature. Again, we're assuming two basic things here. One, the pressure of this gas is being held constant. And two, the number of gas molecules. Are constant. Now, imagine a balloon with some gas molecules in it. And these gas molecules are flying all around, banging into the sides of the container. If I increase the temperature of that balloon, remember that that is effectively increasing the speed of those gas molecules. What that means then is when they hit the side of the container, since they're going faster, they'll deliver a little bit more force to the side of the container. Pressure is force per unit area. So if the force goes up and the pressure has to stay the same, then the area that those gas molecules are hitting over must also increase, so that these two increases can cancel each other out, leaving the pressure the same. Or, as those gas molecules hit the inside of the balloon harder, they can push that side of the balloon further out because of their increased speed. Either way you look at it, as the temperature goes up, the volume of the resulting container must also increase. These two work out to be directly proportional to each other. Volume is proportional to temperature, or if you wanted to say temperature is proportional to volume. And so if we wanted to write a ratio looking at just changing volume or temperature based on a change in the other variable, V1 over V2 would go directly to T1 over T2, because we have a direct relationship here. They go straight across. An application of this is the hot air balloon. It's not a perfect application, but it's kind of a cool application, so I thought I'd let it slide. So imagine an hot air balloon where you have a fire that's heating the air inside the balloon. So these gas molecules start hitting the side harder, but what inevitably has to happen is that some of the gas, because their temperature's increased, their volume must also increase. Now this is where we're kind of breaking the rules a little bit, because what's going to happen is these things try to occupy more space because there's no more space in the balloon, is that they're going to sneak out the side and they're going to occupy space in the normal atmosphere. What that means then is that this gas that used to occupy this space will now occupy, say, all of this space, which means its density is lowered. The amount of mass remained constant, and so with the increased temperature and the increased volume, as the volume goes up, the density had to go down, which means now this balloon, this space, is less dense than air. What that means then is the air surrounding it will try to take its place, and that will create a buoyancy force that allows this hot air balloon to float on the fluid of the air that it is less dense than. So the particles get pumped out of here. As the temperature increases, they try to occupy more space. When they occupy more space, they decrease their density, and a decreased density means that they're not as dense as air, which means that the hot air balloon can float on air. The density of air in the balloon is lower than density out of the balloon. Now, I've been saying that this is kind of a neat application, but it doesn't fit perfectly because in the end, recall, we said that the number of gas molecules should be constant. So these gas molecules fleeing sort of makes this not a really clear, direct application to the law we're talking about, but it's kind of interesting, so I thought I'd include it. All right, for a numerical example, you're blowing up a balloon for a birthday party at 21 degrees Celsius. You tie off the balloon at 4.2 liters. The balloon is then left out in the sun. The sun starts to heat the balloon. If the balloon stretches to bigger than 5.2 liters, it will pop. How hot can the balloon get without popping? So V1 is 4.2 liters. V2, we're going to assume it gets to 5.2 just before it pops, so we'll go to 5.2. And T1 is 21 degrees Celsius. What we want to know is, what is the final temperature at which the balloon would actually pop? So here, because this is a direct relationship, again, I like to put my thing I'm looking for on the upper left-hand side. It just makes it so that my equation is already solved for what I'm looking for. So T2 over T1, and because it's a direct relationship, T2 goes to V2, and T1 goes to V1. Okay. Last but not least, don't forget that we can't be using temperatures in Celsius. We need to use absolute temperature since we're dealing with a ratio. So T1, which was equal to 21 degrees, and that's the temperature in Celsius, I can add 273 degrees to that to get it into a temperature in Kelvin. So that would be 294 degrees Kelvin. Now I can substitute T2, 294 degrees Kelvin, 5.2 liters over 4.2 liters, and I can solve. So my final temperature is 364 degrees Kelvin, which sounds really extreme, but remember, we're not used to the Kelvin scale. So let's convert this back to Celsius so we can see a more meaningful number. Okay, let's just say temperature in Kelvin is equal to the temperature in Celsius plus 273. So 364 is equal to temperature in Celsius plus 273. So my temperature in Celsius is 91 degrees Celsius. So I'm pretty confident my balloon, even if it's left out in the sun, isn't going to get all the way up to almost the boiling point of water, 91 degrees Celsius. So I am not too worried about the balloon popping if it's left out in the sun. We've left a fair amount of growth for it to have without popping, so it should be fine. As temperature increases, the speed of the molecules increases, and so the force they push the side of the container with increases. If the pressure is going to remain constant, then we assume that the container itself will expand, increasing the area, so that the increased force and the increased area cancel each other out, leaving the pressure constant. With a hot air balloon, we can imagine this causing particles to escape the balloon, decreasing the density of the air in the balloon in comparison to the air outside of the balloon, and making the balloon float in the air. And here is a numerical example of where we look at how much expansion will happen with a change in temperature.